Okay, hi guys, afternoon. Okay. That's really, okay, let me try this. Okay. Oh. Okay. Yep. So, I guess it's um, just have just a few things today. See, the assignment 3 is due today. Does anyone have any questions about assignment 3? Okay. Question means it's strong. Um, Okay, so for question 3, let me make some just quick remarks about question 3. In question 3, you only know, here's an example of question 3. We want to have an induction that works like this. Assume P of 0, and assume P of 0 implies P of 1. Assume P of 0 and P of 1 together implies P of 2. And also assume P of 0, P of 1, P of 2 implies P of 3. And then we want to conclude P of 3. Okay, but in the question, it's not 3, it's n instead of 3. Or sorry, it's k instead of 3. Okay, so you can't just use induction. So the trick is, yes, you have to use strong induction, but there's like a trick to it because you only know for now I'll just say there's like a trick to it because you only know that that P of n implies P of n plus 1 for n less than k. Actually, that's different than what I wrote. So here, what you know is this. Okay. But yes, you can use strong induction or whatever induction. And then for question 4, So let's just write out the different statements, what they mean, and see if that gives us any hint. So for n equals 0, question 4 says 1 is greater than or equal to 1 plus 0 over 2. That's what that's the statement for n equals 0. For n equals 1, it says that 1 plus a half is greater than or equal to 1 plus 1/2. For n equals 2, it says 1 plus a half plus a third plus a quarter is greater than or equal to 1 plus 2/2. For n equals 3, it says 1 plus a half plus a third plus a quarter plus a fifth plus a sixth plus a seventh plus an eighth. That's greater than or equal to 1 plus 3/2. Okay. For n equals 4, we have the terms from 1 up to 1 over 16. Well, I won't write them all out, but we have terms like that, and that's where we have to show that's greater than or equal to 1 plus 4/2. Okay, so I hope that you can see the pattern as to what's going on. Well, like the difference between each successive inequality. You know, like on the left-hand side, each time there's twice as many terms, but they get smaller and smaller. And each time the right-hand side increases by a half. So what we have to show is that each thing that we increase by is greater than a half. Okay. So for example, 1/3 plus 1/4. If we can work it out directly, like we put it in lowest terms, you know, that would be like 7/12, which is bigger than 6/12. So it's bigger than a half. I mean, if you calculate this, it will definitely be bigger than a half. But I'll just give you one hint as to like how you can show that this is bigger than a half. And I guess I hope that you can work from there. Okay, that's not good. So for question 4, my hint is that you can look like a 1/5 plus 1/6 plus 1/7 plus 1/8. That's bigger than, actually that's strictly bigger than 1/8 plus 1/8 plus 1/8 plus 1/8. And that's 4/8. That's a half. And then the induction hypothesis in question 4 would say that like, it would say that 1 plus a half plus a third plus a quarter is bigger than or equal to 1 plus 2/2. Now, if we add this inequality to this inequality, that gives you the statement for n equals 3. So we call this star, and we call this star star. Just add, we get star 2 double star. Okay, to get this is a 2, not a plus 0. Okay. Okay, that's just a hint, I guess. Other tips would be to just make sure to use base case, induction hypothesis, induction step conclusion. That sometimes can help you organize what you want to do. Okay. Okay. So, any other questions? Oh, I saw someone type something. When is coursework 1? Okay, so coursework 1 is gonna be wait. Um sorry, I'm just you guys will have to help me. I thought I already scheduled coursework 1 for this class, but now I don't remember if I did it for this class or for abstract algebra. So, oh, that was for abstract. Okay, thank you very much. Okay, so that's good to know. So for this class, so I believe that abstract coursework was supposed to be in about 2 weeks from today. And then for this class, 10th of March. Okay. So with the restriction that it has to be, I have to check my calendar. It has to be at least 2 weeks from today, as the 10th of March. Should put it. March the 16th. Yes. So let me say, I would have put it on the 15th, except we have a really long class on the 15th, so I didn't want that. The exam will actually be 12 hours. And I will try, so start time. I don't want to, I think if it's 10 a.m. to 10 p.m., that is what I want to tentatively say, unless anyone has any objections to that time. I don't want to put it too early in case someone might start work from like 8 to 4 or something. Okay. I can move it a little bit later. Yeah, I can make it 12 to 12. Okay. That's noon. That's midnight. Oh, sorry. Okay. Is everyone okay with this arrangement? Okay. Okay. Topics. This will just be first 3 assignments. Okay, I mean, with respect to work, I would say that if you have like, I don't want the exam to be taking more than about 2 hours. So if you have 2 hours to set aside, that should be enough. Okay, and the topics, I don't remember if I said, but assignments 1 to 3. So I try to give, you know, questions that I put on the assignment that weren't marked. Should try those as practice. If you get through with all of those and you want more questions, you can let me know and I can probably come up with some more. Okay. Okay. Oh, so I've been putting solutions to the questions just as videos. So if you look under the videos, well, there's only 2 assignments so far, so there's only 2 solutions. But if you look under the YouTube playlist for tutorials, some of those videos are assignment solutions. And I try my best to explain how to work things out. Okay. Yeah. Okay. So, we don't have, I don't want to do too much today, but I want to kind of start talking about so yeah, basically we did an example of, we constructed the natural numbers, we proved the principle of mathematical induction, and then we used that to prove that the natural numbers have this property that they're totally ordered. Okay. And then we also use this thing called the recursion theorem to construct addition recursively. Then we proved like n plus m equals m plus n. And then on the 4th assignment, I'll put some questions that are basically like, oh yeah, let me write down first before I keep on talking, but let me just write down coursework 1 topics. Just the topics of assignments 1 to 3. Yeah, okay. Right, so on assignment 4, I might ask you to prove some related things related to addition that you can prove with induction. And there's so many different things you can do with that. You know, I can ask you to prove like these basic things about inequalities for the natural numbers. Lots and lots of stuff. Okay. So we'll see. But now I kind of want to move on. So assignment 4 will kind of continue, at least a little bit, continue talking about natural numbers. But I want to move on and kind of try and briefly describe how we construct the integers, the rational numbers. And then from the rational numbers, we want to construct the real numbers. Okay, and that is going to be our next focus, is like constructing the real numbers from the rationals. Okay. Okay. So constructing the integers from the natural numbers is kind of like an algebraic thing. Okay. Okay. So we want to construct Z, and the problem is the problem that the integers solve is that we want to solve equations basically. We want to solve like for x, n plus x equals m. Okay, and when m is bigger than n, we can solve this. I might put that as a question on assignment 4. Okay, for m bigger than n, there is a solution. For m less than n, there's no solution. Okay, so this is what, you know, so this is a typical algebra thing. We have no solutions, but we want to make up some. So whenever there's no solution for x, well, we kind of like group. Well, we kind of like we look at the ordered pair of n and m. Okay. Whether or not there is a solution. Okay, so here's our idea. Okay. So here's just our idea. That's our idea is an integer is just like this is an informal construction, but our integer is just going to be like an equation that like to solve like n plus x equals m. Okay. That's our integer. And then another integer, y, might be like, here n and m are natural numbers. Okay, another integer might be like an equation like k plus y equals L. Okay, and L will be natural numbers. Okay. And then two integers are going to be equal. Basically, like if the m minus n equals L minus k, and x equals y, if and only if, basically, you know, m minus n equals L minus k, you rearrange everything, m plus k should be L plus n. Okay. Right. And we're trying to construct things so that we can solve equations like this. Well, just pretend you can and describe like when two equations should describe the same integer. And we can also add equations to add integers. So like if we add these two equations, we get n plus k plus x plus y equals m plus L. Right. So we describe an integer is just going to be an equivalence class, but it's going to be like the difference of two natural numbers. Okay, and to add two integers, well, we just add like the differences. But notice like because we only have for natural numbers we can only add, we have to describe everything we do in terms of natural numbers and addition. But you also have things like x minus y. Well, if you subtract these two, well, like let's think about what minus y is. Minus y should just be like L minus y equals k. Okay, so really integers are like kind of ordered pairs of natural numbers. One natural number subtract another natural number. That's an what an integer should be. Okay, so negative y, so if k plus y equals L, then negative y should be L plus negative y equals k. We switch the L and the k to get the negative. Okay, just as an example, the integer 5, you can look at it as like, I'll put it in a box, but it should be like 3 plus 5 equals 8. That's one way to describe it. Or you could describe it like 0 plus 5 equals 5. You can describe it using different equations of natural numbers, but they all give the same integer. Okay, that all describes an integer 5, whereas the integer negative 5 that would be, well, we just switch everything. So these three equations describe the same integer 5. To get the integer negative 5, we just do 8 plus negative 5 equals 3. 5 plus negative 5 equals 0. 6 plus negative 5 equals 1. Okay. So an integer describes just like either the sum of or difference of basically the difference between any two natural numbers. Okay. Okay. And there's many different ways to describe the same integer. So basically we need an equivalence relation, you know. So let's just take just a 5-minute break, and then we'll try and explain like the formal construction of the integers in a not hand wavy fashion, just the formal construction. Okay, but informally, the integers solve the problem of solving an equation like n plus x equals m, where n and m are any two natural numbers. Okay, just like the complex numbers solve the problem that x squared plus 1 has no solution. Well, now we're just solving the problem that like 5 plus x equals 0 has no solution. Okay, so yes, let's just take 5-minute break, come back and talk a little bit more about the integers. Okay.